Right now, as you watch this video, your computer is performing millions of invisible jumps. It pauses what it's doing, leaps to somewhere else entirely, executes a tiny piece of code, then returns exactly to where it left off. Over and over again, millions of times per second. And here's the truly mind-bending part. Your processor, this magnificent piece of silicon, doesn't actually know how to do this naturally. It's like teaching a train that can only go forward how to teleport backwards in time. So how does it work? How does a machine that only understands do this, then do the next thing, suddenly develop the ability to jump around like it's got a mind of its own? Before we dive deeper into this mystery, if you're curious about the hidden mechanisms that make our digital world tick, hit that subscribe button. Because today, we're going to pull back the curtain on one of computing's most elegant solutions to an impossible problem. Every time you click a button, send a message, or even just move your mouse, your computer is calling functions. Hundreds of them. Thousands of them. These are small packets of instructions that your program needs to execute. And here's where it gets interesting. Your central processing unit, your CPU, is fundamentally a sequential machine. It reads one instruction, executes it, moves to the next one, executes that. Line by line, step by step, marching forward like a soldier following orders. It has no inherent concept of jumping somewhere, doing something, then magically remembering where it came from and returning there. From the hardware's perspective, there's actually nothing special about calling a function. The CPU doesn't wake up one day and decide it wants to learn how to jump around. But from the software side, from the compiler's perspective, this is an enormous challenge. The compiler has to generate machine code, actual sequences of ones and zeros, that somehow trick this linear machine into behaving like it has memory, like it has intention, like it knows where home is even after wandering far away. Imagine you're reading a book page by page. Suddenly there's a note that says, "Stop here. Go read page 157, then come back and continue from this exact sentence." Simple enough for a human with a finger to mark the page. But what if you're a machine with no fingers, no bookmark, no inherent way to remember where you were? That's the problem every computer faces billions of times a day. When compiler engineers first tackled this problem back in the 1950s and 60s, they realized they had two fundamental strategies. The first one is almost brutally simple. It's called function inlining. Here's how it works. Instead of having the function exist as a separate piece of code somewhere in memory, you just copy the entire body of that function and paste it directly into every place where it's called. If you call the same function 10 times in your program, you get 10 identical copies of that code scattered throughout your executable file. The beauty of this approach is its simplicity. Your program becomes one long, continuous stream of instructions. The CPU just marches forward, executing everything in sequence. There's no jumping, no returning, no complexity. It's like instead of having a recipe book where you flip to different pages for different dishes, you write out every single step in order. Even if it means writing add salt 50 times throughout your cookbook. But here's the problem. You have a function that's 100 lines of code, and you call it 1,000 times throughout your program. That's 100,000 lines of duplicated code in your final executable. Your program becomes massive. In the early days of computing, when memory was measured in kilobytes and cost more than gold, this was simply unacceptable. Even today, with gigabytes of storage, there are limits to how much code you can realistically duplicate. So the second strategy emerged, function outlining. This is where you write the function code exactly once. Store it in its own dedicated location in memory, and whenever you need it, you jump to that location. Execute it, then somehow jump back to where you came from. This is far more memory efficient. One function, one location, called as many times as needed. But now we're back to our original problem. How do you jump away and still remember the way home? Here's where it gets truly fascinating. Many people assume that processors must have special, magical instructions for calling functions. Instructions labeled call and return that just work by some hardware sorcery. But the truth is far more elegant. You can build an entire function calling mechanism using nothing but a simple jump instruction. Let me show you how. The basic idea is straightforward. When you need to call a function, you jump to its address in memory. When the function finishes, you jump back to where you started. Done. Except, there's a critical flaw in this plan. If a function can be called from multiple different places in your code, how does it know where to return to? It's like telling someone to go to the store and come back home, but you have 5 different houses, and you never told them which one you started from. The first solution that engineers tried was deceptively simple. Before jumping to a function, store the return address in a variable. A specific designated location in memory that says, this is where I need to go back to when I'm done. Inside the function. When it finishes executing, it reads that variable and jumps to whatever address is stored there. Problem solved, right? Not quite. This works perfectly fine until you encounter nested function calls. Imagine function A calls function B, and while function B is running, it calls function C. When A calls B, it stores its return address in our special variable. But then when B calls C, it has to store its return address in that same variable, overwriting what A put there. Now when C finishes and returns, it goes back to B. That's correct. But when B finishes and tries to return, it reads the variable and jumps to wherever C left it pointing, which is completely wrong. A has lost its way home. The program crashes, or worse, it jumps into random memory and starts executing garbage as if it were code. This isn't just a theoretical problem. In the early days of programming, this exact issue caused countless bugs and crashes. Programs would work fine in simple cases, then mysteriously fail when functions started calling other functions. It was like a phone system where only one person could remember one phone number at a time, and every new call erased the previous number from everyone's memory. The solution that emerged is so elegant, so perfectly suited to this problem, that it feels almost inevitable. The stack. If you've studied computer science, you know what a stack is. But let's think about why it's the perfect structure for this specific challenge. A stack is a last-in, first-out data structure. Imagine a stack of plates. You can add a plate to the top, and you can remove a plate from the top. You can't pull a plate from the middle without toppling everything. The last plate you put on is the first plate you take off. Now apply this to function calls. Every time you call a function, you push the return address onto the stack. When that function finishes, it pops the top address off the stack and jumps there. If a function calls another function, the second return address gets pushed on top of the first. When the inner function finishes, it pops its return address, leaving the outer function's address still waiting safely underneath. It's like a tower of breadcrumbs where you always pick up the most recent crumb first, automatically following your path back in reverse order. This is brilliant because it perfectly mirrors the natural structure of function calls. Functions always return in the opposite order they were called. If A calls B calls C calls D, then D finishes first, returning to C, then C finishes, returning to B, then B returns to it, last in, first out. The stack doesn't just solve the problem, it embodies the problem's inherent structure. With this mechanism, you now have everything you need for a complete function calling system. Just 3 elements. A jump instruction to get you to the function. A stack to remember return addresses. And a stack pointer, a special register that keeps track of where the top of your stack is. That's it. From these 3 simple components, you can build arbitrarily complex programs with thousands of nested function calls, and every single one will find its way home. Now here's where hardware engineers saw an opportunity for optimization. In the early days, programmers had to manually manage the stack using regular memory operations and variables. You'd write code to increment the stack pointer, store a value at that location, decrement the pointer when you were done. It worked, but it was tedious and error-prone. So modern CPUs added dedicated hardware support. First came the stack pointer register. Instead of using a variable in general memory, you get a special fast register specifically for tracking the stack. Then came push and pop instructions. Instead of manually calculating addresses and moving values, you just say, push this value or pop into this register and the CPU handles all the details. And finally, as a crowning touch, came the call and return instructions. Here's the beautiful part. The call instruction is really just shorthand for 2 operations. Push the return address onto the stack, then jump to the function. The return instruction is shorthand for pop the top of the stack, then jump to that address. These instructions aren't magic. They're macros, convenient shortcuts that the hardware provides to make assembly code cleaner and faster. Under the hood, they're doing exactly what we described, managing a stack of return addresses. Think of it like this. You could send a letter by manually carrying it to the post office, filling out forms, weighing it, calculating postage, and tracking it yourself. Or you could just drop it in a mailbox and let the postal service handle everything. The call and return instructions are like that mailbox. They abstract away the complexity, but the underlying mechanism, the stack of addresses, remains the same. But calling a function isn't just about jumping there and back. You need to send data to the function, the parameters, and you need to get data back, the return value. This opens up a whole new dimension of complexity. How do you actually pass information between functions? There are two primary methods, each with its own trade-offs. The first is passing data through registers. Registers are tiny, incredibly fast storage locations built directly into the CPU. They're like having information literally in your hand instead of having to walk to a filing cabinet. If your function takes a few simple numbers as parameters, you just put those numbers in specific registers before calling the function. The function reads them from those registers, does its work, puts the result in another register, and returns. This is blazingly fast because registers are the fastest memory the CPU has access to, but registers are severely limited. A typical CPU might have 8, 16, maybe 32 general-purpose registers. And they're small, usually just 8 bytes each. So what happens when your function takes 20 parameters? Or when you need to pass a massive data structure that doesn't fit in a handful of registers? This is where the second method comes in, passing data through memory, specifically through the stack. Before calling a function, you push all the parameters onto the stack. The function reads them from there, does its work, and either returns a value through a register or writes it back to a specific location on the stack. This is slower because accessing main memory takes much longer than accessing registers, but it's infinitely more flexible. You can pass as much data as you want, limited only by the size of your stack. The specific rules for which parameters go in registers and which go on the stack are defined by something called the calling convention. Different operating systems, different CPU architectures, even different compilers can use different conventions. On Windows, a 64-bit x86 processor might put the first 4 integer parameters in specific registers and everything else on the stack. On Linux, the convention is slightly different. These conventions are part of the ABI, the Application Binary Interface, the low-level contract that ensures different pieces of compiled code can actually work together. So let's return to our original question, inlining versus outlining. If inlining seems simpler, why bother with all this stack complexity? Why not just inline everything? On the surface, inlining appears to have clear advantages. There's no pushing and popping return addresses, no jumping back and forth. Less overhead, less complexity. Just straight-line code execution. But reality is far more nuanced. Consider a large function, maybe 100 lines of compiled machine code, that gets called in 50 different places throughout your program. If you inline it, that's 5,000 lines of duplicated code in your executable. Your program becomes massive. It takes longer to load from disk. It consumes more memory. And here's something most people don't think about. It can actually run slower. Modern CPUs don't just execute instructions one at a time. They have sophisticated caching systems. Your CPU has a tiny, incredibly fast cache that stores recently used code and data. If your code is small and compact, more of it fits in this cache. If your code is bloated with duplicated functions, you might constantly evict useful code from the cache to make room for redundant copies of the same function. This causes cache misses, which force the CPU to fetch code from slower main memory, creating significant performance penalties. Have you ever wondered what's really happening inside your computer when you run a program? It's not magic, it's machinery. But it's a kind of machinery so elegant and abstract that it borders on the philosophical. Today, we're going deep, deep down into the rabbit hole of computation to explore the hidden world of function calls, the stack, and the mind-bending concept of recursion. Let's start with something simple, a function call. In programming, a function is just a named block of code that performs a specific task. When you call a function, you're essentially telling the computer, hey, pause what you're doing, go run this other piece of code, and then come back to where you left off. But think about that for a second. How does the computer remember where it left off? If that function calls another function, and that one calls another, how does it keep track of the entire chain of tasks and know how to get back? The answer is a beautiful, simple data structure called the stack. Imagine a stack of plates. You can only add a new plate to the top, and you can only take a plate from the top. This is a last in, first out, or LIFO system. The computer's call stack works exactly the same way. Every time a function is called, the computer places a little package of information called a stack frame onto the top of the stack. This frame contains everything it needs to remember, the local variables for that function, and most importantly, the return address, the exact spot in the code to jump back to when the function is finished. So if function A calls function B, a frame for B is placed on top of A's frame. If B then calls function C, a frame for C is placed on top of B's. The computer is always working on the function at the very top of the stack. When function C finishes, its frame is popped off the top, and the computer uses the return address in B's frame, which is now at the top, to continue right where it left off. Then B finishes, its frame is popped, and we're back to it. It's an incredibly elegant system for managing complex sequences of tasks. This simple mechanism is the bedrock of modern programming. It's what allows us to build massive, complex software by breaking it down into small, manageable, reusable functions. Without the stack, programming as we know it would be practically impossible. It would be like trying to write a novel without chapters or paragraphs, just one endless, unmanageable stream of consciousness. Now, this is where things get really interesting. What happens if a function calls itself? This is a concept called recursion, and it's one of the most powerful and sometimes confusing ideas in computer science. A recursive function is one that solves a problem by solving smaller instances of the very same problem. Think of a set of Russian nesting dolls. To open the entire set, you open the largest doll, and inside you find a slightly smaller, but otherwise identical doll. The process to open this inner doll is the same. You open it to find another. You repeat this process until you reach the smallest solid doll that can't be opened. That's your base case, the point where the recursion stops. Let's look at a classic example. Calculating a factorial. The factorial of a number, say 5, written as 5, is 5 times 4 times 3 times 2 times 1. You can define this recursively. The factorial of any number n is n multiplied by the factorial of n1. So factorial of 5 is 5 times factorial of 4. Factorial of 4 is 4 times factorial of 3. And so on until we get to the factorial of 1, which is just 1. That's our base case. How does the stack handle this? When you call factorial 5, a stack frame is created. To get its answer, it needs to call factorial 4. So a new frame for factorial 4 is pushed onto the stack. This continues all the way down to factorial 1. The stack now has 5 frames piled up. Once factorial 1 hits the base case, it returns the value 1. Its frame is popped. Now factorial 2 can complete its calculation, 2 times 1 and return 2. Its frame is popped. This chain reaction continues back up the stack, with each function completing its part of the multiplication, until finally, the original factorial 5 function gets its result and returns 120. The stack provides the memory for each distinct call, allowing a single piece of code to exist in multiple, nested instances of itself simultaneously. It's a mind-bending dance between code and data. Recursion allows us to write incredibly concise and elegant solutions to problems that would be messy and complicated to solve otherwise, especially problems involving tree-like structures, like navigating a file system or parsing code. But there's a danger. What if you forget the base case? What if your Russian doll never ends? In that case, the function would keep calling itself forever, pushing more and more frames onto the stack until the computer runs out of memory for it. This is a famous error that every programmer encounters, a stack overflow. It's a literal overflow of that stack of plates we imagined. Reflecting on this, it's amazing to think about the pioneers of computing. People like Alan Turing, Alonzo Church, and Grace Hopper weren't just building machines. They were wrestling with the fundamental nature of logic, information, and process. They had to invent these concepts like the stack and recursion from pure thought. They built an entire intellectual universe, a new kind of physics for a new kind of machine. The stack isn't just a technical detail. It's a testament to the power of abstraction. It's a simple idea that unlocks immense complexity. It's the silent, invisible engine that powers almost every piece of software you use. From the web browser you're watching this on, to the operating system running your device, to the games that create vast immersive worlds. Every time you click a button, you're setting off a chain reaction, a cascade of function calls, with stack frames being pushed and popped at lightning speed, a silent, perfectly choreographed ballet happening millions of times per second. It's a hidden world of breathtaking complexity, built upon a foundation of beautiful simplicity. So the next time your program runs, take a moment to appreciate the invisible machinery humming away beneath the surface. The humble stack, tirelessly remembering where to go next, allowing order to emerge from chaos and enabling us to build the digital world we live in today. It's a quiet hero of the modern age. Thanks so much for diving deep with me today. If you found this journey into the heart of the machine as fascinating as I do, consider liking the video and subscribing for more explorations into the world of technology. See you in the next one.